5 things everyone should know about ancient oceans. Number 5. There's a lot we can learn from the tiny things that live in the oceans called foraminifera, or forams.
A planktic foram is a microscopic zooplankton. It's essentially an animal. It produces a calcium carbonate skeleton, and that's what we find that's preserved in the fossil record, because obviously all of the soft body parts that would have been protected by the hard skeleton rotted away, and not preserved in the fossil record.
They look a bit like popcorn. They're very small, microns, so sub-millimetre scale. They are white and globular, so they look like lots of little balls all stuck together. They are a single cell, and they have a hard calcium carbonate wall on the outside, which encases their squidgey interior parts. It's called cytoplasm. And then outside of their shell, they have all of these long frondy strands, and they can ensnare their prey with that. And some of them also have long, thin, needle-like spines all around those, and then they float in the water column. And yeah, in a lot of ways they look like, well, to the untrained eye, they look like tiny little popcorns.
The planktic forams of the Eocene are the most beautiful things you will ever see. They have these really elaborate, large skeletons made up of calcium carbonate. They are microscopic. They often sort of look like little tiny grains of sand to the naked eye. But as soon as you get them under the microscope or more advanced imaging techniques that you can use on them, absolutely beautiful. Foraminifera are important because from this tiny, tiny fossil, because of the sort of advances in the geochemical techniques that we have, not only can we use the fossil to tell us about evolution of life, patterns of change, but we can actually analyse the chemistry of the foram shell. And that shell tells us about how big were ice sheets, how hot was the ocean, what was ocean circulation doing. There are so many different pieces of information from this one tiny shell, and it's because they're so abundant and widespread in the ocean, they really are like the most amazing archive for ancient worlds in the past.
In a sense, they're like little natural records, like snapshots into the past, little windows into past ocean chemistry.
So each foram has a very specific temperature range, salinity range at which it can grow. And so by looking at the assemblage of the different foraminifera that are within that sample, you can unravel the environmental conditions at that time when they were living at that specific point.
Over the last 65 million years, planktic foraminifera we've discovered have one of the best fossil records there is. And lots of other important groups in the oceans, they don't end up in our fossil record, they don't leave a trace of themselves because they've got no hard parts. And that's one of the most important things about planktic forams, is that they do leave a record, and they leave a very good record. So we can pick up high resolution changes in chemistry in the oceans and changes between species as a consequence of the changes in their environment.
And to get hold of these forams, to study them, involves drilling cores of sediment from the bottom of the sea.
Ocean drilling is actually a relatively new phenomenon. It only started, or at least for scientific purposes, it started in about the 1960s. It was started by a group of scientists who were basically fairly bored of what they saw to be sort of quite good but slightly dull proposals that really weren't pushing science forward in any way. And they wanted to do something a bit different that rivaled the space race that was occurring at the time, sort of get people really inspired about geology and the oceans and what you could do with planet Earth. So they outfitted an oil drill ship, and they developed new technologies to try and actually recover sediments from the seafloor, but not just sort of scrape them up. They actually wanted to get cores. Although I should say the sediment cores weren't actually their purpose. Their project was actually called Project Mohole, and they wanted to drill to the mantle of the Earth to see what it was made of. And, it was a very ambitious project. Unfortunately, after 7 years, they didn't get to the mantle. They actually made it a couple of 100 metres through sediment to the ocean crust that lies underneath the sediments. So they got about 2 metres of ocean basalt, and they needed to do about another 2.5 kilometres. So it wasn't entirely successful, but what they did was they completely inspired the current phase of ocean drilling, and they really showed that we could get really good records off of the seafloor and led us to where we are today. And I think that actually without it, the world, and particularly paleoclimate research, would be much poorer for it.